In this video, we're testing the convergence of an alternating series, and so we have to satisfy these two conditions. Okay, and in practice, the first condition can actually be very tricky to show. So I've got to show that when I replace n with n plus 1, I'm going to get something smaller than this term that I'm looking at right now. And for very simple series, it might be clear how to get that done. But for a great number of them, you're going to have to use a calculus trick to get it done. So what I'm going to do, again, the challenge is that it's not obvious that the thing on the left-hand side is less than the thing on the right-hand side because its numerator and its denominator are both bigger. So what I'm going to do here is compare to a function on the real numbers. You could say that's the function that generates these integer terms. And I'm just going to take the derivative of this thing, and if I can show the derivative of this thing is negative, then I know each successive term is going to be less than the one before. So let's get the derivative of this, f prime of x. I'm using the quotient rule here. Derivative of the top is 2x, the bottom left alone, minus the top left alone, derivative of the bottom, over our denominator squared, which would be x to the 6th. Okay, it looks like I can take an x squared out of the entire numerator, so I'm going to cross that out on that term, and I'll kill 2 factors of x on that term, and I'm canceling 2 of those factors in the denominator, so there's an x to the 4th down there now. And that gives me 2x squared minus, if I distribute this 3, minus 3x squared minus 3 over x to the 4th. And that's just negative x squared minus 3 over x to the 4th. Well, negative x squared is negative, and I subtract 3 from it, I get something that's negative, and x to the 4th, that's positive. So this thing is negative. So our first problem is solved. We know the next term is always smaller than the last term. All right, the limit part shouldn't be too bad. So we're going to look at the limit as n goes to infinity of an. So n squared plus 1 over n cubed. And I suppose we'll handle this by just doing the division. So I have n squared over n cubed. That's 1 over n. And the second term would be 1 over n cubed. Both of those things unambiguously go to 0. So we've satisfied the second condition. And to wrap things up, we say, therefore, this alternating series converges.